you all to session 7 of the chapter ray optics. This session will be on thin lens. What actually a thin lens is? Let us check it out. A lens whose thickness is very small. A lens whose thickness is very small when compared to its radii of curvature. A lens whose thickness is very small when compared to its radius of curvature is called thin lens. Okay, understood. Thin lens means a lens which is very much thin, whose thickness is very small when compared to its radii of curvature, right? For example, if I am taking this is a lens, let me call this lens is called as thin lens. What is the thickness? This is the thickness, right? This is thickness, right? Where do I get the radii of curvature? So this is, if I take this is the radii of curvature. If thickness of the lens is very small when compared to the radii of curvature, means we will be getting another one radii here, right? This is the center, and let me consider this is R1 and let me consider it R2. If I compare R1 and R2, if thickness is very small, then this kind of lens is called as thin lens, right? So thickness is very small when compared to radii of curvature. A lens whose thickness is very small when compared to radii of curvature, that kind of lens is called as thin lens. So in this chapter, whatever lens we will be discussing, all those are thin lenses now here, right? We will be considering thin lens and continuing with the other concepts now here, right? Okay. Now, what is the formula for thin lens? Let us check it out. That formula, let me call it as thin lens formula. Let me call it as thin lens formula, right? We have already discussed with the mirror equation. Right. So what was mirror equation? I think you remember that 1 by f is equal to 1 by u plus 1 by v. That was the mirror equation. Now we are finding the equation for lens, that too particularly thin lens. Okay. So that, let me write under the side heading thin lens formula. Right. So this formula we get in the derivation of lens maker's formula. Right. In the last session we have derived lens maker formula, and these were the last steps of that derivation, right? Hopefully you remember, after this step we took object is at infinity, right? If object is at infinity, image will be forming at principal focus, then u is equal to infinity, v is equal to f, and if I substitute that, we will be getting 1 by infinity is 0, so 1 by f is equal to, right? So if I am checking out these two equations, both the right hand sides are same, right? RH is same, LHS must be same. Then shall I say like this, 1 by f is equal to 1 by v minus 1 by u, and this equation is called as thin lens formula. Okay, shall I write like this, 1 by f is equal to 1 by v minus 1 by u, and this formula is called as thin lens formula, where what is f? That is focal length of the lens, right, which I am using, focal length, right? If I am using convex, focal length is positive. If I am using concave, focal length is negative, right? So f is focal length. What is u? U is object distance, right? And what is v? V is image distance. Do remember this, right? So this formula is called as thin lens formula, right? Shall I remind you what was mirror equation, so that we can study comparatively. Mirror equation that we have already dealt. What is the equation for mirror? Mirror equation we got like this, 1 by u, f is equal to 1 by u plus 1 by v. This equation is called as mirror equation. We have already derived it, right? So this equation is called as mirror equation. This equation is called as lens equation, that too thin lens equation or thin lens formula. Just compare it. Here we have 1 by u plus 1 by v. Here we have 1 by v minus 1 by u. Just used to be comparatively, right? So this is the equation for mirror. This is the equation for lens, that too particularly thin lens, right? So this equation or this formula is called as thin lens formula, right? Okay. Now we will be discussing about linear magnification as we had discussed it in case of mirror. Now we will be discussing about linear magnification, right? So let me take next one, that is linear magnification. We know that linear magnification, we write it as small letter m, right? So what is linear magnification, right? It is the ratio of height of the image to the height of the object, simple, right? It is magnifying how much the image has been magnified, right? To know that, we need to calculate linear magnification. What is linear magnification? Ratio of height of the image to the height of the object is called linear magnification. Right? So this is the same definition that we have studied in case of mirror now here, right? Okay, so what is the formula? So let me check it out. Linear magnification, it is denoted by small letter m. So what is the formula? Height of the image divided by height of the objects, right? So this equation is called as linear magnification, and we can write linear magnification in terms of object distance and image distance. Let us check it out that, right? For example, let me consider a convex lens now here. Let me check it out here. So this is a convex lens and this is the principal axis. Okay. Now I want to take object and image and let us check it out. What is the linear magnification? How much do I get? Right? Let me take object here. This is the object. Shall I take? This is the object and this is the height of the object. Right? Height of the object. It is in the upwards to the principal axis. That's why we can take it as positive now, right? This is height of the object. Okay. First of all, where do I get the image? We have learned that how to find image formed by the convex lens now here, right? So this is convex. Let us check it out. First, we need to draw a line which is parallel to principal axis, right? After refraction, where do it go now here, right? So it moves, it passes through the principal focus, right? We know that when a parallel ray of light passes through the convex lens, it converges at principal focus, right? So this is the first ray. Okay, then how to find the image? We need to take a second ray which passes through the optic center now here, right? Okay, where is optic center? This is optic center. Let me take like this, right? Okay, the second ray we need to take in such a way that it should pass through the optic center, right? So this is optic center. Okay, where do I get the image now here, right? So this is the first ray, this is the second ray. They meet at this point, and what is this now here? It is the image of this object, right? What is the height of the image? Let me take it as hi, right? What is linear magnification? Hi divided by HO, right? Height of the image divided by height of the object. But I want to find what is the linear magnification in terms of object distance and image distance. Come on, tell me. Here it is object, here it is optic center. What is object distance? Shall I take it as U? U is the object distance, right? Distances are always measured from optic center, right? So this is object distance and this is, what shall I say now here? Image distance, right? Image is here and we need to measure the distance from optic center. So this is V is the image distance. Okay. Now, if I check it out, let me name them. A, B the object, right? Okay. The image, let me take it as A dash, B dash. Let me take like this. A dash, B dash is the image, right? Okay. Now, I will be considering two triangles. First triangle, let me take ABO, right? Okay. Since triangle, what is that now here? Triangle ABO. Where is ABO? This is ABO, right? Let me consider one triangle in which we have height of the object and triangle which has height of the image. So what is that triangle? O B dash A dash. Let me take this triangle, right? O B dash A dash. Okay, see here? ABO. This is the triangle which I am considering. Next, O B dash A dash. This is the triangle which I am considering. Okay, come on, tell me. If it is angle theta, this is also angle theta. Yes or no? right? These are vertically opposite angles, right? So if this is angle theta, this is also angle theta. This is 90 degree. This is also what we say here, 90 degree, right? If two angles are 90 degree, these two angles are equal, then these two angles must be equal. That is why we can say that those two triangles are similar. Okay, since triangle ABO and triangle OB'-A' are, what shall I say now here, similar, right? We know that if two triangles are similar, then the ratio of the corresponding sides are equal, right? Okay, ratios of the corresponding side. Okay, shall I take like this? So do remember, I took two triangles here, right? Which is that triangle, first triangle, let me take like this. So this is the triangle which is that ABO, and another one triangle like this. And this is the thing, and this is, right? So let me take B'-A'. This is height of the image, and this is height of the object, and this is object distance, and this is what we say here, image distance, right? Okay, we know that these two triangles are equal, vertically opposite angles. These two triangles angles are 90 degrees, and other angles must be equal here, right? So they are similar to each other. Shall I say ratios of the corresponding side? Come on, tell me, what is the corresponding side of B'-A'? The corresponding side of B'-A' is AB, right? So they are corresponding to each other. Shall I say like this? So what is that now here? B'-A'. Corresponding side of B'-A' is AB. That is equal to, come on, tell me, what is the corresponding side of OB'? BO, right? These two are corresponding sides. These two are corresponding sides, hypotenuse, right? Okay, shall I say like this? What is the corresponding side of OB'? Right? So divided by, what is corresponding side of OB'? That is BO. Let me take like this, BO. Come on, tell me now, what is B'-A'? Come on, tell me, what is B'-A'? What is the distance? That is HI. That is height of the image. Is it positive or negative? It is negative because it is downwards. Right? If the distance are measured downwards from the principal axis, we need to take it as negative. That is the sign conventions what we are using here, right? Okay, let me take it as minus. What is AB mean? AB is height of the object. So shall I take it as HO? That is equal to, come on, tell me, what is OB'? Where is OB'? This is OB', right? OB'. Come on, tell me, OB'. So I am moving from optic center to the image. So I am moving in this direction. Is it in the direction of incident ray or opposite direction to incident ray? It is in the direction. So shall I take V, positive or negative? Positive. So let me take it as V divided. Come on, tell me, what is BO? BO means distance are measured from optic center. So I need to take the distance from this to B now here. So I am moving in this direction, that is opposite to the direction of incident ray. So I will be taking it as negative. So what shall I take now here? That is minus M, right? So this minus will get cancelled. What do I get now here, right? So HI divided by HO, that is equal to, what do I get now here? V divided by U. Do remember, what is HI divided by HO? This is nothing but magnification, that is V divided by U now here, right? Shall I substitute that here? Do remember, magnification is HI divided by HO or V divided by U. Do remember this. Right? What is V? Image distance. What is U now here? Object distance. Right? So we got with magnification, that is image distance divided by object distance. It can be calculated by using height also. Height of the image divided by height of the object. But it can also be calculated by using object distance and image distance. So what is magnification? That is V divided by U. Do remember, that is image distance divided by object distance. If you remember the magnification formula, linear magnification formula in case of mirror, right? I think you remember that. That is magnification in case of, what shall I say now here? Mirrors, right? So let me remind you, what was the formula? That is mirror, that is equal to, this is the definition, height of the image divided by height of the object. But what was the equation in terms of U and V, right? Here you got minus. Do remember, right? Minus V divided by U. This is the case in case of mirror, and this is the case in case of lens. Do remember, right? In case of lens, we don't have negative sign here, right? V divided by U, it is positive, but in case of mirror, it is negative, right? Minus V divided by U, right? This is the definition, height of the image divided by height of the object, that is equal to minus V divided by U, right? This is in case of mirror. Just for the comparison's sake, I took this formula. Remember this is linear magnification, right? And another thing, what you need to know here is, linear magnification is positive for erect image. erect image. If the image is erect, or we can call it as upright, right, then we get magnification as a positive, right, and linear magnification is negative for inverted image, right. If the image is inverted, then we get it as m as negative, right. You do remember this, right. Image, as we know that if we were calculating in case of a convex lens, this was the object and this was the image, right, height of the image. So this is height of the object and this is height of the image, right. So this is which kind of image do we get from convex lens, which I had already drawn the ray diagram here. Here we got it as HI here, right. So this kind of image is called as inverted image. If I take inverted image, what is the sign of HI? Minus. What is the sign of HO? Plus, right. So definitely you will be getting m as a negative for inverted image. And if I would have taken the concave lens, right. So if I had taken concave lens, image would have been like this. This is height of the image. If I calculate height of the image, the height of the object, you would have got magnification as positive. So do remember, magnification, that is linear magnification, is positive for erect image and linear magnification is negative for inverted image. So these all that you need to remember about linear magnification. Now let us move on to the power of a lens, right. We speak about what is the power of a lens. First of all, you need to know what actually a lens do now here, right. If you take a convex lens, it converges the parallel rays of light. If you take a concave lens, it diverges the parallel rays of light. Now we will be speaking about power of those lenses now here, right. What is the power of a lens? Power is the ability of a lens to converge or diverge. The ability of a lens to converge or diverge the rays of light incident on it. The ability of a lens to converge or diverge the rays of light incident on it is called power of the lens. Okay, what is the power of the lens? Power is nothing but it is the ability of a lens to converge or diverge the rays of light incident on it. Okay, let us check it out how actually it does now here, right. If I take a convex lens now here, let me consider convex lens. Okay, there is a convex lens like this. This is a convex lens, and if I am taking let me take a thin lens now here, right. Okay, these are the rays which incident on the convex lens. Let me take like this, right. It converges, it moves ahead now here, right. It converges at this point. Let me consider, right. So it converges at this point. These are the rays incident on the convex lens, right. It converges at this point and it converges here, right. Let me consider it converges here and let me consider it converges here. This is the first lens. Right, let me take the second lens. Okay, let me call this is a lens A now here, right. Let me take a lens like this. This is a lens. Just you see what are the difference between these two lenses now here, right. If I'm taking a lens here, right. Now, if I'm taking a parallel rays which are incidenting on it, right. So these are the parallel rays of light which incident on it, right. So it converges at this point. If I'm considering here, it converges at this point here, and it converges here, and it converges here. Okay, just to observe what are the difference between these two lenses, A lens and B lens. This also converges parallel rays of light. This also converges parallel rays of light. Which will converge more? Which lens has more ability to converge a lens? Right. If we compare A and B, right, it converges at a far distance. It converges at a short distance. By this, I can say that the power of B is more than that of A. Right, means it converges more compared to that of A, right. If I want to make the comparison of ability to converge, I will be using a physical quantity called as power. By this, I can say that power of B is greater than power of lens A, right? By this we can see that it converges more, it converges what we say here, less now here, right? So if I'm comparing the ability to converge, B has more ability to converge now here, right? And also if you check one thing, this point is called as principal focus and this point is also called as principal focus. Come on, tell me, what is this distance called over here, right? This is optic center. This distance is called as focal length. And what is this distance now here? This distance is called as also focal length. If I compare the ability to converge, shall I say like this? Ability to converge is it directly proportional to focal length or inversely proportional to focal length? As focal length has been decreased here, the ability has been increased. Means the ability to converge and focal length are inversely proportional to each other. Shall I say like this? 1 divided by, what shall I say now here? Focal lengths. Right? What is the ability to converge? That is called as a power. Power is inversely proportional to what shall I take now here? Focal length. If focal length is more, the power is less. Means power and focal length are inversely proportional to each other. Right? Okay. So the ability of the lens to converge or diverge. So shall I say like this? Then we get the formula for power of the lens. The formula for power of the lens is 1 divided by F. Right? So this is the formula for power of the lens. Right? What is power of the lens? It is the ability of the lens to converge or diverge the rays of light incident on it. So that is called as power of a lens. How to define it? We got a formula now, power of a lens. P is equal to 1 divided by F. Shall I say like this? Power of a lens is defined as power of a lens. The question will be, I'll ask like this: what is defined power of a lens? So we know that we define a physical quantity by using its mathematical equation, that is P is equal to 1 by F. So power of a lens is defined as reciprocal of its, what is that now here? Focal length. Reciprocal of its focal length. So P is equal to 1 by F. So power of a lens is defined as reciprocal of its focal length and conditioned that this focal length must be measured in SI unit, that is meter, right? So whenever we use this formula, we need to know that the focal length should be measured in meter. Then this formula holds good. So power is equal to P is equal to 1 by F. It is defined as the reciprocal of its, what we say here, focal length. Now we will be considering what is its SI unit. Okay, what is the SI unit of power of the lens? The SI unit of power of the lens is diopter. So do remember this, and it is denoted by capital D, right? So diopter is the unit of power of the lens. Shall I say like this? 1 diopter is equal to, if I make it as 1 by meter, shall I say like this? Per meter, right? 1 diopter is equal to 1 per meter or simply per meter now, right? Okay, so if I'm comparing these two, we will be getting like this, 1 per meter, right? So whenever we discuss about SI unit, first of all we will be defining that SI unit. Okay, let me define this now here. Power of a lens is said to be 1 diopter. Okay, when do you say the power of a lens is said to be 1 diopter? The power of a lens is said to be 1 diopter. If I want to make it as 1, F should be 1. What is F? Focal length. What is its unit? Meter. If a lens has a focal length of 1 meter, then the power of that lens is called as 1 diopter. Is said to be 1 diopter. Let me tell you, power of a lens is said to be 1 diopter if its focal length is 1 meter. Right? So power of a lens is said to be 1 diopter if its focal length is, what is the focal length here? 1 meter. If you take a convex lens whose focal length is 1 meter, then what is its power? Then it is 1 diopter. Right? Okay. Power of a lens is said to be 1 diopter if its focal length is 1 meter. Right? So this is the definition of 1 diopter. Do you remember? The SI unit of power of a lens is diopter. When you go to the eye specialist, so he will be subscribing you one glass now here, right? So he says that, okay, you need to wear this kind of glass of this diopter. If you see the slip, you will come to know the doctor will be writing your glasses in terms of diopters now here, right? So according to the diopter, the lenses has been manufactured now here, right? Okay, do remember diopter is the SI unit of power, and the power of a lens is inversely proportional to its focal lengths, right? Okay, now let me define in other way now here, right? Let me take now here, let me take note points. Okay, let me take one let us define the power of a lens in terms of angle now here, right? This is a convex lens, right? This is optic center. Okay, let me take, this is the ray of light, right? So what do a convex lens do? It converges, right? It converges at this point. Let me take this point as what we say here, F, right? Okay, what is this distance? This distance is what now here? Focal length. Let me take this angle, let me take it as delta, right? Okay, can I say what is the formula for tan delta? Okay, shall I say this distance OF, let me take now here A now here, right? This distance, let me call it as H, right? What is the formula for tan? Tan, opposite side divided by adjacent side. What is the opposite side of delta? H. What is adjacent side? F, right? So by this equation, I can find what is the power of the lens, right? What is power of lens? 1 by F. Okay, this will become 1 by F if this distance, incident ray distance, will be what we say here, 1 meter. If the ray of light hits the convex lens at a distance of 1 meter from the optic center, then we can call this tan delta as what we say here, power of a lens. Okay, shall I write like this? Power of a lens is also defined as, we can say like this, it is also defined as, right? So we have already studied what is the definition of power of a lens. It is the reciprocal of its focal length, right? So we are defining it in terms of angle here, right? So power of a lens is also defined as tangent of the angle. Tangent of the angle. It is defined as tangent of the angle. What is that angle? Delta. Tangent of the angle by which, okay, tangent of the angle by which the lens converges, by which the lens converges the ray of light, converges the ray of light. See, angle by which the lens converges the ray of light now here, the ray of light falling at a distance, of what we say here, 1 meter. See here, if the height, that is the distance of the incident ray from optic center, this distance is 1 meter, then that tangent of the angle is called as power. So shall I say this as power, because 1 divided by F is nothing but power. So what is power of a lens? Power of a lens is also defined as tangent of the angle, right? Tangent of the angle by which, right, the lens converges the ray of light falling at a distance of, okay, falling at a distance of, what is this distance? At a distance of 1 meter. From where now here? 1 meter from optic center, right? From optic center, the incident ray, this distance, if it is 1 meter, do remember, if this distance is 1 meter, then this tan of the angle formed, that gives what we say here, power, right? So this is the another definition of a power of a lens, right? If the question is asked, define power of a lens, you can simply tell that power of a lens is the reciprocal of its focal length, and its SI unit is diopter. Now let us understand when the power of a lens will be positive and when the power of a lens will be negative. Okay, do you understand? Power of a lens, power is positive, right? Power of a lens, let me take like this, power of a lens is positive for, come on tell me, when do the power of a lens is positive? We know what is the formula for power. Power is equal to 1 divided by f. Power will be positive if f is positive. What is f? Focal length. For which lens focal length is positive? For convex lens, right? In the similar manner, shall I say like this? Power of a lens is positive for convex lens. Do you remember? And power of a lens is negative for which lens? Concave lens. Okay. Why it is negative for concave lens? Power is negative because focal length is negative, right? If focal length is positive, power is positive. Focal length is negative, power is negative. Do you remember? For convex lens, focal length is positive, therefore the power is positive. For concave lens, focal length is negative, and therefore the power of the lens is also negative. And this is all about power of a lens. Now let us move on to the next session, that is combination of thin lenses in contact. Now what I will be doing? I will be combining the lens. If I combine the lenses, what happens to the focal length? Let us check it out. So that we will be seeing under the derivation of combination of thin lenses in contact. We will be deriving the expression for the equivalent focal length, right, of the combination of the lenses now here, right? Okay, so this is a derivation. Let us start with the derivation. Okay, so we need to take thin lenses. Let me take two thin lenses which are in contact with each other. Okay, let me take like this. Okay, so these are the two thin lenses. If I am taking, this is the principal axis. Let me consider this is the principal axis, and let me consider two thin lenses. Okay, this is the first lens, and let me call this lens as A, and there is another one lens, and these two lenses are in contact with each other. So this is the lens what we say here, B. Its focal length is f1 and its focal length is f2, right? Okay, now so what happens when we combine these two thin lenses? Let us check it out. And let me also take an equivalent lens now here, right? Let me take a principal axis, and let me consider one lens which is equivalent of this combination. Let me take like this. To understand, let me take the equivalent lens, right? For example, this is lens A, and this is the lens B now here, right? So this is the equivalent lens. Shall I say like this? And the focal length of equivalent lens, let me call it as F equivalent, right? So this is the equivalent lens, right? So this lens is equivalent, what we say here, lens. So what is the meaning of equivalent lens? This produces same effect as that of combination, right? For example, if I am considering like this now, right? If I am considering 5 rupee coin and 5 rupee coin, right? If I combine 5 rupee coin and 5 rupee coin one side, and if I am taking a 10 rupees note on another side, both are equal. 10 rupee note is the equivalent of this 5 rupees and 5 rupees. In the similar manner, this lens is equivalent of the combination of these lenses now here, right? Okay. Now let me begin with the derivation. Consider two thin lenses. So we are considering two thin lenses of focal length, which are the focal length f1 and f2, right? So consider two thin lenses of focal length f1 and f2 in contact. In contact means these two are in contact with each other. Now here in this derivation, I will be using lens equation, that is thin lens formula or thin lens equation. Let me take like this. Using thin lens formula, right? We know since these are thin lenses, I can use thin lens formula. Okay, what is that thin lens formula? We know 1 divided by V minus 1 divided by U is equal to 1 divided by F. So that is thin lens formula. Okay, so now I will be taking thin lens formula. 1 divided by V. So what is the meaning of V? That is image distance. That is image distance minus 1 divided by, what shall I say here? Object distance. Right, that is equal to 1 divided by, what shall I say now here? Focal length, right? So this is formula is called as thin lens formula, that is 1 divided by V minus 1 divided by U is equal to 1 divided by F. That is what I have written there, right? So using this equation, that is 1 divided by image distance minus 1 divided by object distance is equal to 1 divided by focal length, that is thin lens formula. Now, as we have already dealt with lens maker's formula, this derivation will be simple and it is analogous to that now here, right? Okay, now let me take an object here. Okay, come on, tell me, if I am taking object here, right, I am considering this is incident ray, right? This is incident ray. If at all, just remind what I have already told you in lens maker's formula. If at all this lens was not there, B lens was not there, image would have been got in this position, that is I dash. Since B lens is also there, so it converges more and we get the image at what we say here, I. This is what we have done in lens maker's formula, same thing, right? There we took two spherical surfaces, here we are taking two lens, that is the difference, right? Derivation is one and the same. There I had used refraction at spherical surface formula, here I am using thin lens formula, that is the difference, right? Okay. See here, come on, tell me what is O, that is the object. What is I, image of the combination. What is I dash, image of the first lens, right? Okay. Then shall I call, if I am taking this is which distance now here? Object distance. Shall I call U now here? What is this now here? That is image distance. Shall we take like this? Then what is I dash? Let me take it as X, which I had already taken now here, right? So let me take, this is the image of the first lens. So let me take, what is the distance now here? X. Now, let me use this formula for both the lenses, for lens A and as well as for lens B, right? Okay. Let me take like this, refraction for lens, what we say now here? A now here. We are using thin lens formula. Let us find what is the refraction at lens A now here, right? Refraction for lens A now here. For lens, let me take it as A, right? So I will be considering the refraction for lens A, means I am considering only lens A now here, right? If I am considering only lens A, okay, this is what I am doing, and for this let me take what happens with the thin lens formula now here, right? Refraction for lens A, right? Okay, now in the absence of lens, let me take like this, in the absence of lens, which is that lens B now, right? Let us consider B is not present at all, right? Same that of lens maker's formula, right? In the absence of lens B, image I dash is formed at distance. What is the distance now here? X, right? In the absence of this lens, image is formed at I dash. Okay, in the absence of lens B, image I dash is formed at distance X. At distance X, image I dash is formed. Come on, tell me now here. For lens A, what is the object? O is the object. What is the image? I dash. Do you remember? I dash is the image for the first lens. When you take second lens and keep, the image shifts here, right? So image I dash, object is O. Okay, shall I use thin lens formula? Yes. Let us start with the derivation here, right? Let me use this equation here, right? So 1 divided by, come on, tell me what is image distance? Since it is an image, what is this image distance? X minus 1 divided by, what is object distance? That is U, right? So that is equal to 1 divided by focal length of lens A. This is a lens A, and what is its focal length? F1. Let me take it as F1, right? So this is equation number 1. Now similarly, let me take for refraction. Let me take for lens. What is that now here? B. Let me take what happens for the refraction at lens B. Okay. As I already told you, if the lens B is kept here, right, what is the incident ray? This is the incident ray. Do you understand? This is not present at that time, right? I am considering this is the incident ray. If this is incident ray, where is object? You cannot see object here, but you can see the object at this position. So I have already told you, I dash plays as the role of virtual objects, right? So I dash is the virtual object for lens A now here, right? Okay, since we are not having this now here, right? Since we are not having the object at this position, but we have object at that position here, right? Okay, for example, if I'm taking like this, right? Do you remember? If at all second lens was not there, it would have been gone like this. Since second lens is there, we got here. So what is the incident ray? This is the incident ray. Okay, this is incident. Here there is no object, but you can take this is as the object. And what is that object? That is virtual object, right? Okay. Now, for refraction at lens B, I dash, let me take now here, image I dash acts as which object now here? Virtual object. Image I dash acts as virtual object forming image. Okay, where is image formed by the second lens? I at a distance. What is the distance now here? That is V, right? So do remember, for second lens, I dash acts as a virtual object which forms image at I, right? Let me take like this. I is the image formed, right? Okay, so one thing what you need to understand, what is I dash? I dash is the image of the first lens and virtual object of the second lens, right? Okay, now come on, tell me, what is the formula? 1 divided by image distance. What is image here? This is image and this is object. What is image distance? V. Shall I say like this? 1 divided by V minus 1 divided by object distance for this lens, which is the object I dash, virtual object. What is the distance now here? X. Let me take it as X. That is equal to 1 divided by focal length of lens B. So this is the lens B, and what is its focal length now here? Let me take it as F2, right? So this is equation number 2, right? So I will be adding these two equations now here. Let us check it out what happens now here, right? Okay, now if I add these equations 1 and 2, what do I get, right? So let me take now here. Let me continue with the derivation now here. So adding equations 1 and 2. Okay, let us add equations 1 and 2. What do I get? Let me write this first. 1 by x minus 1 divided by u. This I have written, let me write here. Plus 1 by v minus 1 divided by x. That is equal to 1 divided by f1 plus 1 divided by, what shall I say here? f2, right? So here, this will get cancelled. What do I get now here? 1 by v minus 1 divided by u is equal to 1 divided by f1 plus 1 divided by f2. Okay, let me take this is as equation number 3 now here, right? We got equation number 3. Now, let me go ahead. Now, I will be considering, what is this? This is equivalent lens. Considering equivalent lens of focal length. What is its focal length? F equivalent. Considering equivalent length of focal length, F equivalent, right? So let us consider this is a lens which produces, say, considering equivalent length of focal length F equivalent, which produces same effect as that of what we say here, combination, right? Considering equivalent lengths of focal length F equivalent, which produces same effect as that of combination, means its effect is same as that of combination, right? The effect of 5 rupee plus 5 rupee is nothing but effect of 10 rupees, right? In the similar manner, what is equivalent length? Which produces same effect as that of combination. Now, let me take the equations now here, right? If I am considering here, it is an object, right? It falls here. What is the image of here? Right? It produces the same effect. What is the image now here? Here. What is this now here? This is object distance. And what is this now here? This is image distance. So this is the effect of the combination, right? Okay. Now, let me use thin lens formula for this now here, equivalent. What is thin lens formula? 1 divided by image distance. What is image distance? This is the image. What is image distance? V minus 1 divided by, what is object distance? U, right? So this is object distance, that is equal to 1 divided by, what is focal length of this now here? That is F equivalent. Let me take it as equation number 4. Now comparing equations 3 and 4. Okay, let us compare these two equations 3 and 4. If you see here also 1 by V minus 1 by U, here also 1 by V minus 1 by U, right? Left hand sides are equal. Understood, sir? Right hand sides will be equal. So what do I get? 1 divided by F equivalent, that will be equal to 1 divided by F1 plus 1 divided by F2. Right, 1 divided by F equivalent is equal to 1 divided by F1 plus 1 divided by F2, and this is the expression for equivalent focal length of the two lenses in contacts, right? So this is the derivation, right? So 1 divided by F equivalent is equal to 1 divided by F1 plus 1 divided by F2, and this is the derivation. Derive the expression for equivalent focal length of two thin lenses in contact. The question will be asked like this, and this is the way you need to derive. So we got with the expression 1 divided by F equivalent is equal to 1 divided by F1 plus 1 divided by F2. Now let us take some note points about combination of thin lenses. Okay, first one, if more than two lenses are in contact, right? We have seen if two thin lenses are in contact, what is the formula? 1 divided by F equivalent is equal to 1 divided by F1 plus 1 divided by F2. So this is the derivation which I had done here, right? So now if you take more than two lenses are in contact, if more than two thin lenses are in contact, then the equivalent focal length, of the combination, okay, see, if more than two lenses, understood, thin lenses, right? Okay, if more than two lenses are in contact, then the equivalent focal length of the combination is given by, let me take equivalent focal length is given by 1 divided by F equivalent, that is equal to 1 divided by F1 plus 1 divided by F2 plus 1 divided by F3 if there are three combinations. If there are more than three, so in the similar manner we need to continue, right? So this formula remains the same, right? So if there are two lenses, 1 by F1 plus 1 by F2 is equal to 1 by F equivalent. So if more than two lenses, 1 divided by F equivalent is equal to 1 by F1 plus 1 by F2 plus 1 by F3. If there are more, okay, again the formula continues like this, right? So let me write this in terms of power of the lens. Okay, if I write in terms of power of the lens, what is this? This is equivalent power is equal to the power of the first lens, because you know power is 1 divided by focal length, right? 1 by F is nothing but power of the first lens plus power of the second lens plus power of the third lens, and it continues, right? So this is the formula for equivalent power of the combination of lenses, right? If I take only two lenses, then equivalent power is equal to power of the first lens plus power of the second lens, because we know 1 divided by focal length is nothing but power, right? So in terms of power, if I write P equivalent is equal to P1 plus P2 plus P3 dash like this, right? Okay, now let me write this in terms of magnification. In terms of magnification means linear magnification, right? So M equivalent, that is in terms of magnification, linear magnification, the formula will be like this: M1 into M2 into M3 into like this, right? Here we get multiplication if you consider the linear magnification, right? So these are some of the note points about combination of lenses, right? This combination of lenses is used in optical instruments like telescope, right? if you see the telescope, there are more than one lens, right? There we will be using combination of lenses. So they are used in telescope, and they are also used in microscopes. They are used in camera, and they are also used in binoculars. Right, so these are the optical instruments, right? There are many optical instruments in which we will be using more than one lens. We will be combining the lens, and we will be using, and the equivalence focal length of the combination of the lens is given by this formula. And this is all about combination of thin lenses or thin lenses in contacts. Right. So we have derived the formula for equivalent focal length, and we have also seen in terms of power as well as in terms of magnification, and this is the end of lens. Thank you.